I'm going to be talking about some work that we've been doing with my co-author Ken Longenecker here at the Bishop Museum. And what we're doing is looking at life history information for three commercially important reef fishes and hoping to use that information to evaluate the effectiveness of marine reserves as fisheries management tools. So I'm just going to give a brief overview of the purpose of our study and go more into reproductive data because that's what we've been working on lately. So these are the three species that we're working on. Initially we chose just to work on the Potter's angelfish, and the title of our proposal was this rapid low-cost analysis of life history information. And Hickory came back and said, well, if it's so rapid and so low cost, why don't you add some more species? So great. Okay. So the Potter's angelfish was a very popular aquarium fish, most collected aquarium fish here on Oahu, so that was a safe bet. We already had that. We then added the mini-bar goatfish, or moano, because it's a popular food fish collected with spears and also hook and line. And then as a third choice, very quickly, we added Dacilus because we thought, well, let's not make it too difficult on ourselves. We know there's life history information for this available, so we won't have to reinvent the wheel. But in retrospect, it may not have been a great choice because the reported fishing for this species isn't very much compared to the Potter's angelfish. And it also isn't that abundant in either of our study sites. So we may be removing that later on. Okay, so our study has a couple of different components. Before we can compare the effectiveness of marine reserves as fisheries management areas, we need to know some life history information from the fish that we're looking at. And this is information such as size and maturity, the relationship between age and size, and also fecundity relationships. As many of you know, fecundity of fish really increases greatly with fish length. So a very large fish will produce many more times eggs than a very small fish. We also needed to collect demographic data. This is information on relative abundance and also information on size structure. And we were going to compare between a marine reserve and a fished area to see if there's a difference. Once we have this information, we can add in our life history data and get estimates of mortality, natural mortality and fishing mortality in the marine reserve and in the fished area. And we can use this to get estimates of production. And by production, I'm looking at excess biomass produced in a year and also reproductive output. One of the ways that marine reserves are proposed to enhance local fisheries is by the export of eggs and larvae into adjacent fished areas. So they're seeding these areas and keeping them stocked with eggs and larvae. So we wanted to evaluate that. Once we have these two production estimates, we can then go back to management and see whether the current management techniques are working or whether we need to institute some sort of alternative management regime. Okay, so most of you all are familiar with by now how we obtain age data from fishes. There's some bones inside the head called otoliths, and they tend to lay down rings on a regular basis. Some of the fish we look at lay down annual rings, some of them lay down daily rings. For the three species in our study, we're looking at daily rings. So we take out the otoliths, we etch them with acid and put them on SEM and just go crazy counting hundreds and hundreds and hundreds of rings. Once we have this information, we can then plot an age length distribution and find out the relationship between age and size. Now this is very important because later on we'll be collecting size data from a marine reserve and from a fished area, and we'll want to convert that back to age to get mortality estimates. So this demographic data that we collected, we used a technique called laser videogrammetry. A lot of times when people survey fished areas for fish sizes, they can estimate fish size just by eyeball, and it takes a lot of training to do that. And neither one of us had that training, so what we did was mount two parallel lasers onto a video camera, and because the lasers were parallel, any fish that we filmed, we would superimpose a scale of, here's about 30 millimeters, and we could take frame captures from this video footage to estimate the size of the fish that we saw in our transects. Here's our sample area. We compared Hanauma Bay, it's been a marine reserve for about 40 years now, to an adjacent fished area in Maunalua Bay. We chose an equivalent area of about 38 hectares for survey, and we did, I think, 17 linear surveys in Hanauma Bay and 23 in Maunalua Bay, giving us a total sample area in both places about 13,500 square meters. Now we chose Maunalua Bay because it is a very highly fished area, both pole and line for example, for the goatfish, and it's also one of the top collecting areas for Potter's angelfish. So if there was a difference in biomass or in production, we expected to see a clear difference between these two areas. And this is the data that Ken showed you last time. So these are preliminary estimates on production in terms of eggs and larvae for the three species inside and outside of reserve. Again, this information is going to change when we put more of our video data back in there and also update our life history parameters. One of the things that stood out very quickly is that we didn't have a greater production of either biomass or eggs inside the marine reserve. It wasn't significantly greater as we would expect if marine reserves are doing their job in augmenting the production of fish. And again, this is just for these three species. They're not typical species like manini or things like that that we think of that are really abundant inside Hanauma Bay. I'm going to back up and talk about some of the reproductive information that goes into these estimates. To estimate the reproductive output for fishes, we need to know things about abundance of the fish, the size structure, because size is related to fecundity, and also something called that size at maturity, or L sub 50. Okay. The size at maturity is the size at which 50% of the individuals are reproductively mature. And initially, we got our information at size and maturity from literature records before we had a chance to actually look at the gonads ourselves. For the Potter's angelfish, there was a great paper by Marv Linetsky looking at histological sections of their gonads. And looking through his data, we were able to estimate a size at maturity of 45 millimeters for females and 82 for males. Now, this is a sex-changing fish. It changes from female to male, and it also occurs in sort of female bias groupings of the average ratio is about 3 females to every 1 male. For the goatfish, we had very little life history data available. Based on the DAR poster, which lists size and maturity, we estimated it would be 185 millimeters, but we couldn't find a paper that linked to this data. We also didn't know anything about the sex ratio of this species, and so we just supposed that, well, maybe it's 1-to-1 for the comparison that you saw previously. Okay, so how do you figure out what the size and maturity is for a fish? Because it has a lot of implications, both for management and also for estimating production of eggs and larvae. In a large body fish, you can remove the gonads, you can look at them and probably tell whether they're ovary and testis. And sometimes you can even determine whether or not the ovary is reproductively mature just by looking at the size of the oocytes. This becomes much more difficult for small bodied fishes, and you can never truly know whether males are reproductively active without doing histology. So we did histology. We took out the gonads, we embedded them in plastic resin, and we sectioned them on a rotary microtome, stained them with either hematoxylin or eosin or toluidine blue. Our first job was to classify these gonads as either ovaries or testes, and then evaluate the reproductive function of the gonads, determine whether or not the individuals they came from could function as male or female.